Hello statistics class. This is the first video I've made in my shop since we were out last spring. So this is a really important chapter. This chapter is the culmination of basically the last 4 chapters. In an introductory statistics course, which is what this one is, which is like a freshman level college course, which is why you can get dual enrollment credit for it. This is the pinnacle of what we're after. This is the peak. Every other course, if any of you take any other stats courses beyond this in college, everything is going to base itself pretty much on this topic, this hypothesis testing. A lot of this stuff, it's the peak of where we're going, and I think it's really important that you understand the basic logic of what's happening here. So the first hypothesis test that we're going to look at is the 1 proportion z-test. And I'm going to focus on 2 different methods. But today, since this is the very first kind of lesson in hypothesis testing, we're just going to worry about 1 method for now for probably about a week or so. And then I'll throw another method at you, and then you'll be free to use whichever method you want. So we're going to be using the traditional method today. And if you watched the other YouTube videos that I posted on Google Classroom, these 3 steps should look familiar. We're going to write a ho-ha, we're going to create a null model, we're going to calculate the test statistic, and we're going to think about what's happening here. So you're going to see a whole bunch of little stuff coming together. The stuff that I'm going to put on the board behind me, none of it's going to be new until the very end when we make our decision. Nothing is going to be new. It's everything that you see is going to be things that are on the board that have been on the board before earlier in the year. Everything is going to be there. All right. So the very first thing is we have to create this ho-ha. So if you watch those videos, the HO, which we kind of call the HO, this is the null hypothesis. The null hypothesis is the boring hypothesis. It's what's already happened. You can think of the HO as like it's the original hypothesis. Some books will call it the original hypothesis. The HA is the alternative. It's the alternative hypothesis. So the HO and the HA are very important. The HO, the null hypothesis, or the original hypothesis, is from the population. Both of these are from the population. Nothing here is about a sample. The ho-ha is always about the population. And that will be given to you in the problem. From the ho and the ha, we're going to get whether we have a right tail test, a left tail test, or a 2-tail test. I'm going to talk about that here in just a second. But first, we're going to formulate our null and our alternative hypotheses. Okay? So, this is the first step of any hypothesis test. The very first step. So we have 25% of Bradford County likes seafood. Well, right there, that statement, that's your null hypothesis. So P equals 0.25. Where did we get that? A former study. Maybe that's from 10 years ago. And you want to find out, has that increased? Has this increased? Question mark. A very good question. Now, you're sitting in a statistics course. I hope that you would not be so naive as to think, well, we'll just conduct another sample, and if that sample says more people, more than 25% like seafood, then that must happen. I hope you're not that naive, because that's what a lot of people think. They say, well, just do another survey, and if more than 25%, then it did go up. No, we can't be that naive about things, because what if we sample 50 people and all 50 people like seafood? Conversely, what if we sample 50 people and none of them like seafood? we have to do what, a sampling distribution, a pile of p-hats. And we have to get that empirical rule going and all that good stuff that we've learned the last 3-4 chapters. So, the alternative hypothesis is right here. Has this increased? Is P now greater than 0.25? We want to answer this question. That tells us what kind of test we have. The ha tells us what type of test. If the ha is greater than, it's going to be a right tail test. If the ha is less than, it's going to be a left tail test. If it does not equal, it's going to be a two-tail test. What do they look like? Here. There's your normal curve. Boom. What's a right tail test? Are we out here? Look at the right tail. See how clever we are? Left tail test will be less than. Are we over here? Are we in here? Two-tail test is both of them. Okay? What's a two-tail test? Most of you can probably figure out what's a left-tail test sound like. Has this decreased? Duh. What's a two-tail test sound like? Has this changed? Because if it changed, it could be a two-tail test. You could be on the right side or the left side. You could be one or the other. So the HA, the alternative hypothesis, what we affectionately call the ha tells us what type of test we're going to have. Whether we're working on the right tail, the left tail, or both tails at the same time. Okay? So, I'm just going to erase that so we have a little bit more space here. That's a very simple concept. And when you take your next quiz, that'll be a question. How do you know what kind of test we're doing, and connect it to the ha? Right there was the answer. Greater than, less than, not equal to means right tail, left tail, two tail. It's a very, very simple connection to make. Okay? So, next thing, we have to create a null model. Well, earlier I said, well, this thing is a pile of p-hats. Remember? We got all these p-hats. Because why? Because it is a sampling distribution. So we have this pile of p-hats. And that pile of p-hats makes that normal curve. So what's smack dab in the middle of all those p-hats? The true p. So that's the central limit theorem. And the central limit theorem says that the mean of all those p-hats is the true p. Now you might remember that catchy thing when we were doing the means, which will be the next hypothesis test we do, where we always said the mean of the means is the mean. But this time we're doing p-hats. So the mean of all the p-hats is the true p. The mean of the sampling proportions is the population proportion. Because remember, p-hat, sampling proportion. True p, population proportion. Well, we're talking about the population here. We haven't even begun talking about the test statistic yet. How come? Because I haven't given it to you yet. We can do 2/3 of this problem without that information. And I'm going to give you that information here shortly when we get to that step. So the mean of the p-hats is the p, and the standard deviation of that sampling distribution of p-hats is, do you remember the formula? Maybe you're looking at your card. Okay? It is just square root of p times q over n. That should look familiar to you. Why should it look familiar? Because we did it 2 chapters ago and we did it last chapter. Anytime we talked about p-hats, boom, it was there. So the standard deviation of all those p-hats. The standard deviation of that picture is the square root of pq over n. Notice we don't even need a p-hat yet. P-hat doesn't appear in the formulas. Okay? So we're going to create our null model here. Our null model. So, all of this in the box, this is number 1 up there. Boom. All of this right here. Now we're going to make a null model. The null model is going to be right here, number 2. Okay? The null model. What the null model says is we're assuming that the null hypothesis is true. And then we're going to take a sample and we're going to compare it to that null hypothesis, and we're going to make a decision and say, is it still true? Or are the results so crazy that we would say, I don't think so. Because randomly that's not going to happen. So let's make a null model. Null model is simply another normal curve. What's in the middle? Remember, this is a sampling distribution. This is a sampling distribution of p hats. Otherwise known, what we always said in class, it's a pile of p hats. And where do they all like to congregate? Right in the middle, at the true p. Remember, this is a whole bunch of p hats. So the null model, the true p, what is the true p numerically? 25%. P, right here it says p equals 0.25. So this is 0.25. Now, what did we always like to do whenever we had a normal curve? Empirical rule, mean. 68, 95, 99. We learned that back in October. We always like to do that. Why do we like to do that? Because it governs everything we do with a normal curve. As long as the population is randomly distributed and it's normal-ish, and it's bigger than 30, and all that other criteria that we talked about, but we have 68, 95, 99. Very, very important. And what's the most important of those 3 numbers? 95. 95 is the most important because that's 2 standard deviations from the mean. And if you're beyond 2 standard deviations, you are called, I hope everyone's saying outlier, because that's what you are. So, we got to go up. 1, 2, we're going to go out 3. 1, 2, 3. So you might remember, well, this is 1z, 2z, 3z, negative 1z, negative 2z, negative 3z. Okay, not a problem. Well, we got to fill numbers in because we have to make a decision, and we haven't even got to that step 3 yet. We're still making the null model. So 0.25. 0.25 is p. Now we have to calculate the standard deviation because we have to know how far up we're going every time. So p is 0.25. Okay? P is 0.25. What's q? Well, you should be able to answer that. P plus q equals, I hope you're saying 1. P and q are complements. They have to add up to 1. So that means q 0.75 divided by, n. I didn't give you an n in the problem yet. I have to give you that. So, it says here, use an alpha level. This is alpha 0.05. We'll get to that in a few minutes. But let's take care of this. How about we say, I think on my little practice problem here, I said, let's say 20 people out of 50 now like seafood. This would be in the problem. That's the information that I omitted from my original write-up of the problem up there. 20 people out of 50 like seafood. So what this is a pile of p hats. It's a collection of 50 people at a time. Every p hat is a collection of 50. So you go around, you ask these 50 people, ask these 50 people, ask these 50 people, put all their data here, boom, boom, boom. All these p hats are falling all over the place. Remember, these are all p hats. And they're piles of p. It's a pile of p hats and it's a pile of 50 people. So n is 50. Okay? So 0.25 times 0.75 divided by n, take the square root. I already have that calculated. It's 0.06. Okay? So this is 0.06. Now that's not that difficult of a calculation. So 0.06. So that means my first z-score is 0.31. My second z-score is 0.37. And And my third z-score, I'm way out there now, 99.7%, 0.37 plus 0.06 is 0.42. Okay? What if I go down? 0.25 minus 0.06 is 0.19, this is 0.13, and then this is what, 0.07. Okay? So my standard deviation, the standard deviation of all these p-hats is 0.06. Okay? I'm just writing that there because I want to erase this so that we have more room to write. Okay? So that's the null model. It's a pile of p-hats. It's a whole bunch of p-hats. And every p-hat is a collection of 50 people that we have asked, hey, do you like seafood? Do you like seafood? Do you like seafood? It's all these 50s. So we have it all on here. So now that's 20 out of 50. 20 out of 50 has nothing to do with the population. 25% of people like seafood. That's population, P. Has it increased? That's P. This is all population. 20 people out of 50, so the population stuff, that was maybe from 10 years ago, somebody did a study. Now we want to see if it changed. Did it go up? Well, how do we know if it went up? We're going to ask these people, 20 out of 50. From one sample of 50, we can make a really good decision on whether it went up or not. So, 20 out of 50. 20 out of 50 is p-hat. And what's p-hat? P-hat is the sample proportion. This is otherwise known as the test statistic. Now, why is it called the test statistic? Test because that's what we're testing. We're testing the hypothesis. Does this p-hat tell us has the amount of people like seafood increased, decreased, or stayed the same, or whatever? Why are we using the word statistic? Well, from chapter 1, way back in September. Statistic is something you calculate from the what? From the sample. So p-hat, the test statistic, is 20 out of 50. 20 out of 50 is the same as 2/5, which is 0.4, or if you like 0.40, to be consistent with the two decimal places up here, then go ahead 0.40. Okay? So this sample, this p-hat from our sample is 40%. So if you're naive, you might say, well, 40% is higher than 25, so yeah, it went up. Okay, but what if you were like, what if it wasn't so high? Like, what if you got 30%? And it was only up, it was only up just a little bit. We're going to get to that. So, where does 0.40 fall on here? Well, 0.40 is right in here. 0.40 is right in here. So the basic logic here is this. Is our test statistic so extreme that if we assume the null hypothesis is true, that is so extreme that it must have changed? Well, look at where we're at. We're between 2 and 3 z-scores. Well, what if we change 0.40 to a z-score so we can look at it as a z-score? So let's change this 0.40. So how do we calculate a z-score? A z-score is p-hat minus the true p divided by the standard deviation. So p-hat's 0.40. The true p is 0.25. Standard deviation is 0.06. So I have that calculation run over here. 0.40 minus 0.25 divided by 0.06. That is a 2.5 z-score. And guess what? We are right between 2 and 3. So 0.40 is 2.5 z. We are sitting right here. I'll put a big old dot right there. So I hope that you're thinking now, because we just did calculate TS. TS stands for test. Calculate the test statistic and think. The thinking is what's going to get you. You know why? because some of you are going to overthink it and you're going to get yourself all confused. Is 2.5z, what is 2.5 z-scores called? I hope that you're thinking, Mr. Lascanon, that's an outlier. It is an outlier. But what's our boundary value? Well, we can't use 2z because remember empirical rule, mean, 68, 95, it came from the center. If we use empirical rule, mean, 1, 2, 1, 2, there's 95%, but all of this was left open. So we had 95% in here, but the two tails were left open. Well, this is not a two-tail test. What kind of a test was this? We said it was a right tail test. Why was it right tail? Because greater than on the ha, so we're only worried about this right tail. So we have to back that down a little bit. So we want 95% to be from the left, all up through here, shade all this in, and then we have to come in about right here. Well, what is this magic boundary value? Well, these magic boundary values have a name, and you've heard this name before. It's called a critical value. We did it last chapter when we did confidence intervals. Critical Z. We did critical Z-scores, and we did critical T-scores. And nobody likes to T when we do a T-test because it always changes with the population. But the Z-scores don't. Critical Z-scores stay the same with the population. So you might be thinking, well, I remember that number was 1.96. Well, 1.96 was when we came from the center and we went out. Boom. Remember, we're going out from the middle. We're not going out from the middle this time. We're coming from the far left. So everything that I shaded here is 95% of the graph. What's over here? 0.05. And guess what? That 0.05, in hypothesis testing lingo, we call that the alpha value. Alpha is the significance level. The easiest way that I can explain what is the significance level, folks, is the complement of the confidence value, confidence level. So what's the most common confidence level that we worked with last chapter with confidence intervals? It was 95%. What were the three most common? 90, 95, and 99. What did I tell you about 90? It's stupid. It is silly because it's statistically insignificant. The only two that really matter are 95 and 99. So, likewise, the best two significance levels that you can have in a hypothesis test are a 0.05 and a 0.01. And that 0.05 reflects this open tail. 5% of this is this open tail. If your test statistic falls in that region, this open region, we're going to call that the rejection region. If your test statistic falls in the rejection region, the reject region, if it falls in there, which ours does, then what do? We reject, that's why we call it the rejection region. We are going to, this is our conclusion. Here's our conclusion. I'll write it big right down here. Here's our conclusion. C:, reject the null. Now, we're going to talk more because in 3 days, today's Monday, so hopefully by Thursday, I see all of you in person in our classroom. There's a whole lot of nuances that we'll talk about in the context of the problem, how to state the conclusion. But since this is like first crack through it, I just want you to get the idea down. So we're just going to say, for right now, we're just going to say, we're going to reject the null. Okay? So we're going to reject the null. Now, what does rejecting the null mean? It means we're saying this null hypothesis, P equals 0.25, we're saying it's probably not true. Now, why am I saying probably? Well, because we did this with a significance level of 0.05. What have I preached to you since we begun inferential statistics? Nothing is absolute. Well, I don't want to say that. Remember we talked about the snowfall problem and calculating a confidence interval, and I said I can give you a 100% confidence interval for tomorrow. It's going to snow between 0 and 400 inches, and all of you are like, well, yeah, I could say that too and be right every day of the year. Yeah, so I guess that is absolute. But if you're taking samples and you're making a pile of p-hats, our test statistic is way out here. You would not expect it to fall in here. It's not falling in here. So since it's out there, it's in the rejection region. So what we're going to say is we're going to reject this p equals 0.25 and say, you know what? It's probably not true. If you wanted to attach like a percentage on it, you would say, well, 95 samples out of 100 are going to support it, but this is one of those samples that's in that rejection region, so it's one of those samples that's really extreme. So we're just going to say, okay, our null hypothesis is probably not true. Probably not. Okay, now, what is this value here? Because we're starting away from the left and we're not centering it at the mean here, and remember, it's not going to be mean 68, 95, 99.7. It's more like, well, we're starting from this end and it's 0 all the way up to 95. So it's not going to be 2 z-scores. And we learned last chapter that that critical value for 95%, some of you might remember it was 1.96. So it wasn't exactly 2, and we talked about that for a long time. It's not exactly 2. So what is this value? It's 1.645. Okay, so a significance level of 0.05 is a z-score of 1.645. If we're on a left tail test, it's going to be negative. Now, where are we getting that 1.645? It's on your table. And I will show you that when we get back on Thursday. But for right now, I'm sure you can believe me that it's 1.645. It's because you have to take 95%. If you look at your table right smack dab, when it says 0.950, there's going to be a little star, and then there's going to be an arrow going to 1.64 because it is such a very, very special place on the table. Okay, we'll talk more about the critical values when we get back in person. Okay, I'll give you the chart of the basically six or nine that you're going to need. Okay, and we'll put them on our formula cards. But 1.645, you're going to see that a lot. So basically you're comparing, are we in that rejection region? Yes. If you're in the rejection region, you reject the null. Now what happens if you're not in there? What happens if this was over here in a shaded spot? What if you were like in here? Well, then we wouldn't say the null is true. We would say the null, I guess you could kind of think of it as it's probably going to still be true, but our language is different. We're just going to say, well, we're not rejecting it, so what's the opposite of rejecting? We're going to fail to reject the null. So I've always explained it, and I'm sure a million other statistics teachers have explained it, kind of like if someone goes to trial, you know, just because they're not guilty doesn't mean they didn't do it. So it's like, well, if you're found not guilty, does it really mean you didn't do it? Well, not necessarily. So it's kind of the same thing here. If you're inside here, we're just going to say, well, we're going to fail to reject it this time. And why are we going to fail to reject it? Because our test statistic supports the null being true. It just happened to fall in there randomly, so we're just going to say, well, this time, with this particular p-hat, under these conditions, we're not rejecting. We're failing to reject. So the null is probably going to be true, but we're not really going to say that it's true. We're just going to say we're failing to reject it. So until we get further evidence, this null, we're going with this null. We're sticking with it. But in this problem that we did, we were out here in the rejection region. So what would a left-tailed test look like? A left-tailed test would have this open area on the left. What would a two-tail look like? Two-tail's different. You're going to have different critical values. It'll be open on both sides, and then your test statistic will fall somewhere, one of three places. We're not going to tackle the two tails until we return in person, and we can clean this up. So for right now, I want you to try, let's try another problem really quick. Actually, you know what, we'll make that a second video. So for right now, just try to absorb this, try to digest it, and then I'm going to make another video and we'll just do another problem. So until then, I hope that you're getting your mind wrapped around this. It's a whole bunch of little stuff coming together with really a decision criteria at the end. Okay? Hang in there, you'll get it. Everybody always freaks out the first 2-3 days we do hypothesis testing, but then after about 2 weeks, everyone's like, "Oh, well, this is actually kind of easy." And I think you'll probably feel the same way. All right. So until next video, hang tight.